Welcome to another episode of the ASEP podcast. So today we will be talking with Jernej Barbič, who is a full professor of computer science at the University of Southern California in Los Angeles. He is originally from Slovenia, but he has lived in the United States for the last 23 years. He has published over 50 publications in top journals in his field. Besides successful academic career, he has also co-founded and led a successful technology startup called Ziva Dynamics. He is also a Sloan Fellow, and in 2011, MIT Technology Review named him one of the top 35 innovators under the age of 35. His research interests include computer graphics, computational mechanics, applied mathematics, interactive physics, medical imaging, biomedical and neural networks, digital humans, film visual effects, haptics, virtual reality and the Metaverse, intellectual property law, and many more. Thank you for joining us today, and I hope that we can cover as many of these fields of interest as possible.
Thank you, and thank you for such a nice introduction. I know it's a long list of topics, so maybe a little more difficult to read and remember. Okay, but yeah, thank you for the introduction. Happy to be here.
Very nice having you. So I would like to start with asking what motivates you to work and be continuously interested in all of these fields, and what are some of the pivotal moments or maybe projects that shaped your research direction?
Well, so I would say that I am something that you could call a mid-career scientist. So I've been around for a while, in this field, and this long list didn't just happen overnight. This evolved through my life, through my continued interest, certain events that happened along the way. So what motivates me? Well, first of all, I just absolutely love science. I love discovery. I'm excited by mysteries. I want to reveal the mystery, discover new things. And so it's natural for me to, work in science. And the fields are many just because I have many interests. I've always had many interests ever since in high school, also later at university. Of course, one has to focus on something, right? You have to focus on something and explore that field in some depth in science. But I generally like many topics, and I like to contribute to many parts of our society. And that's why I seek applications in many diverse fields. Even though primarily you could say that I work in computer science and in computer graphics, what keeps me motivated is to find applications of my work. So use what I'm doing, use the mathematics and physics to do good, to improve the world, to improve the life of others, also my own life, but also the life of others. That's always been my main motivator. And that's what really engineering really is all about. Engineering is about improving the lives of others. That's really fundamentally what it is. That's not my quote. This is the quote from the United States National Academy of Engineering. So what was your question? What pivotal moments shaped my research direction? Well, I can give a little bit of a history here for how I ended up doing, what I'm doing. So in high school, which was in Slovenia, I went to Gimnazia Tolmin. I am from a small town in northwestern Slovenia called Most na Soči. I love mathematics and then decided to study mathematics for undergraduate. I did this at the University of Ljubljana, which was a wonderful, amazing, strong program in mathematics. Here in America, I sometimes say that it's this Russian-style mathematics, this very hardcore, good quality mathematics that gave me the foundation for everything that I do today professionally. So I love mathematics, I love the depth, the beauty of it, but I was also searching for applications. I wasn't satisfied just by somebody saying, well, this and this algebra may be applied in this and that context. I wanted to actually see exactly how mathematics could be applied and where it could be applied. And so towards the end of my undergraduate degree, I started wondering whether I should stay professionally in mathematics or should I maybe try some other field. At the time, this was at around the year 2000 when I was finishing up my undergraduate degree in Ljubljana. There was this field, which was not a new field at the time, but it was still much younger than mathematics. That was computer science. And I was drawn to it because I could see how I could use mathematics to do computer science. But at the same time, I saw all of these technology stories that were coming from America, many from California, about Silicon Valley, about these companies like Microsoft, Apple, that were building this amazing technology. And I became very interested, about this field. And I also loved computers. I love to program, design programs. And so it's natural to to switch because I saw that there's going to be more real-world applications in computer science than in mathematics, and I could still use a lot of mathematics so I could satisfy my intellectual curiosity. And so I made this decision to do computer science for my doctorate degree. I was always very motivated. I knew that I will probably be a professor, so at least that was my motivation. And so then I switched over to computer science. At the time, there was a very influential person in my life. That was Jernej Barbič, who is nowadays a full professor at the School of Mathematics and Physics at the University of Ljubljana, Facultetea za Matematico in Fisico. And he had done something similar before me. So he was also a mathematician who did a PhD in computer science in America. So first of all, the fact that he even existed and did this path encouraged me to pursue the same. And also when I was applying to Carnegie Mellon, he helped me in getting admitted. So I'm still very, very grateful to him for this. I think he's an amazing professor. So that was one pivotal moment. Then when I actually got admitted to a few schools in the United States and also Canada, they were all in computer science departments. And so then there was this other episode where I flew to Pittsburgh, Pennsylvania. This was circa in year 2001 because they paid for me to come to Pittsburgh for them to see the school and make up my mind whether I even want to go to America and see the professors and all that. This was 6 months before I actually started my PhD. So when I was in America, I met several professors at Carnegie Mellon. This is in Pittsburgh, Pennsylvania. It is one of the top 3 computer science programs in the world, even to this day. The other ones would be MIT and Stanford. And so I went to CMU and landed in Pittsburgh. And I was completely shocked culturally because the country was very, very different from Europe. And so I talked to many professors, but there was one professor that especially made a lasting impression on me. And that was Professor Egon Balázs, who was a professor of mathematics and operations research actually at the business school at Carnegie Mellon. But I signed up to meet with him one-on-one because I thought that his work in operations research was relevant. I've TA'd operations research at the University of Ljubljana in that year. So I showed up at his office and we discussed mathematics, but also life, and also we discussed his career path. And so I was there in his office and there was this pivotal moment where he started asking me about mathematics, and at the time I already finished my undergraduate degree, right, at the University of Ljubljana. I was this young guy who really, was kind of, versed. I mean, I knew mathematics, right, because I had just finished, 5 years of undergrad in mathematics. So he was asking me questions about this and this and this theorem, and I was able to answer everything that he asked, and he was just talking to me. And then the man at the time was already over 70 years old, and he was originally from Romania. And he looked at me, and at some point I said, well, I'm not sure whether I should come to America or not because it's so different and so on. And then he looked at me in the eye and he said, and he put his hand onto my shoulder and said, you should come back. Right? Come back meaning because I was about to go back to Slovenia and make up my mind whether I want to come to America. And he said, you should come back. You belong to America. And that was this one very pivotal moment where I, kind of felt it inside me that, yeah, this is what I needed to hear. It was the final push, that made me go. And so then when I went back to Slovenia, I accepted the Carnegie Mellon's offer. And 6 months later, I went to CMU and enrolled as a computer science student. Computer science PhD student. And then I stayed there for 6 years. During that time, I first did a little bit of computer science theory, but then soon there was this wonderful professor that CMU hired. That was Doug James, who became my mentor. And he was doing essentially applied mathematics, but applied to computer graphics, physically based simulation, everything visual computing. So he was really, really good, a very, very ambitious scientist who gave me very difficult problems to solve. And then we went on and solved, some problems during my PhD. It was like really, really hardcore, rigorous training. The entire school was wonderful also, all the professors, and maybe not really literally all the professors, but there was a lot of good stuff. I learned really a lot at Carnegie Mellon. I was essentially transformed from being a mathematician into being both a mathematician and a computer scientist. Because I've taken many classes in computer science and so learned about artificial intelligence, architecture, programming languages, databases. So I really obtained a broad computer science education. So I ended up being both a mathematician and a computer scientist. Then when I was finishing up my PhD, I was applying for some faculty positions and I nearly got one. This was in 2007 at the end of my PhD. And that would have been at McGill in Montreal in Canada. There was a situation there that they had two candidates and one of the candidates was Canadian and I was not a Canadian. And they have a law in Canada that if you are, or a guideline that if there is two candidates that are equal for faculty, they have to prefer the Canadian citizen. So the job went to the other guy and I was a little disappointed, but okay, that's life. So I'm just saying these are these kind of semi-random moments, right? Where you may end up in one country or in another country, depending on these kind of seemingly trivial reasons. So then I was very interested in industry already at the time. And to be honest, when I finished up my PhD, I wanted to be a professor, but there was a part of me that also wanted to engage with computer graphics industry. Right? I wanted maybe to just be a professional in industry, be like a high-tech, advanced developer, coding up the algorithms that I learned during my PhD into actual practice. So that would have been a nice, career, intellectual, stimulating career. So I was considering pursuing that career as well. So I applied to this film studio in San Francisco called Industrial Light Plus Magic that many of you might have heard of. So this is the very famous company in San Francisco that made many films over the years and innovated and continues to innovate technology for film. So the Terminator movies, for example, the visual effects were done by them. Many really famous movies. So I applied to them and I interviewed and I was offered an actual position. So the interview was successful. I was offered the job and I would have been in their advanced character group, essentially coding up math and physics algorithms to do high quality humans and animals and other digital creatures for film. This is what would have been my daily job had I taken that job. But at the same time, there was this professor that I got to know over the years when I was at Carnegie Mellon. His name is Jovan Popovic. He's originally from Serbia, but like myself, he's been in America since a very young age. And he was at the time faculty at MIT. And he said that he likes my work. Actually, it happened because I applied to be a professor at MIT. And they looked at my faculty application, and that year I think they didn't hire anybody in computer graphics or anything, but he was inspired by what I wrote and called me up and asked me if I want to be his postdoc. So I ended up having these two kind of dream positions, right? One kind of arguably the top or one of the top positions in industry that you could get in the field of using computer graphics for film versus obviously a top university continuation of research. And so I decided to go to MIT just because I decided that maybe being a professor, I enjoyed that a little bit more than going to industry. So I ended up being a postdoc at MIT, where I continued my research in computer graphics with Jovan. This was for 2 years. And then at the end of that, I applied again to be faculty. And there is a little lesson here to learn, and that is that you have to be persistent in life. That if something doesn't work out the first time, you have to try again and again and again. And I think that's what separates very successful people from the ones that are not so successful. That the very successful ones keep trying. And they keep trying because they're so driven, right? They're so driven. They know what they want. They're very motivated and they keep trying despite the rejections. So I tried the second time, and that time I got more interviews than the first time around. I had an interview in Switzerland at EPFL to be faculty. And actually, at EPFL, something very similar happened to what had happened to me before at McGill. And that was that, again, I was a finalist and there was two candidates and I was not chosen. The other guy was chosen. And in that case, it was because the other guy had already been in Switzerland in academia for several years. He was also several years more senior than myself. He had a longer file. I mean, he's a very, very strong researcher. So in that moment, he probably deserved to be chosen. He had on record, right? If you look at the record, he had more publications, so he was given the position. And but I won the position at USC, University of Southern California in Los Angeles, which is where I'm still today. So I've been here for 15 years, since 2009. There was at USC, again, some pivotal moments or pivotal people. I think actually moments is a little overrated in life. I think the biggest things that happen to us is through interaction with other people. That's, at least in my life, has been the case, that it was always through meeting somebody or connecting to somebody or really getting along well with somebody that my career progressed to the next level, or that something important happened that helped me, kind of unlock the next level, if you will. And at USC, there was this professor of robotics called Gaurav Sukhatme, who was already a very established, internationally very established, super well famous professor of robotics, who had such amazing charisma. When I came to USC during the interview, met him with one-on-one, that it was just awesome, amazing to talk to him. And again, he radiated positivity and really made me realize that I'm joining some amazing department. I mean, I knew, of course, USC is not a bad school. I mean, USC is one of the top 20 computer science departments in the United States and arguably also in the world. Right? Okay, maybe in the world it would be maybe top 30, something like this. Right? And just in America, just for perspective, there is 200 computer science departments that offer a PhD. And in the world, there is hundreds, if not thousands. Okay? So being at the top 20 or top 30, I know everybody thinks, I have to be at the very best one, but it's still very, very good, right? You still get very good research conditions. You get amazing students. The other faculty are all very strong. So he incited me to join USC, and I joined USC, became professor, and he became my faculty mentor formally. So I was able to meet with him quite often as a young assistant professor, and he would give me advice on how to survive in academia, what to do if in my class I have a difficult student who's completely unreasonable, how to deal with the situation, how to apply for funding, how to do successful research. He was very, very generous and shared all of this with me. Nowadays, he is actually the vice dean of the entire Viterbi School of Engineering. So he was another pivotal person in my life. And then maybe, since there is many people that affected me, maybe I would want to mention just one more. And that was James Jacobs, my future co-founder of Ziva Dynamics. With him, we met in 2011. This was when I was already a professor of computer science at USC. And I went to an academic conference, ACM SIGGRAPH, which is the annual computer graphics event, the biggest, most prestigious computer graphics conference in the world. So I went there and I was presenting a paper that I wrote together with my PhD student in my lab at USC. And so after I finished presenting, there was this guy that walked up to me and congratulated me on a good presentation and just started talking. And I looked at the tag, of this person, and it said Weta Digital. Weta Digital is a highly sophisticated, amazing, advanced technology company from New Zealand, from Wellington, the capital of New Zealand. And they are famous for many movies. So they are like I would say, together with ILM, they would be traditionally, at least historically, they would be the top two companies that do visual effects for film in the world. I mean, nowadays there is many others, but traditionally those two were, I think, in my opinion, the most visible one, the most famous ones. So I saw Weta Digital on his stack, and I was like, great, somebody's from industry, they're talking to me, so they want to know something about me. So he asked me a bunch of questions about my work, about the paper that I had just presented. And then he also told me that he knows my software library, Vega FEM, which is something that I guess we will talk about more in this interview a little later on. So he was using it in industry. He downloaded it and was using it. And he was very happy about it and wanted to know more about it. So, I was at the time already busy. There was this conference, other things. And I could have just said, well, okay, nice to meet you. I got to move on to this another thing. But something inside me was telling me that I like this person, that this person is asking me good questions. And I was a little honored, that somebody from Weta is talking to me. So I just continued talking, and we kept on talking about technology and specifically about my work and about that software. And then we ended up talking for 3 hours without stopping, which is a little crazy, I guess, now that I think about this. And we went to some hotel room lobby, after half an hour, and continued talking for 2.5 hours. So we really, really got along very, very well. That is my future co-founder. I made the company, right? 4 years later, we co-founded the company together, Ziva Dynamics, but that's how we met. And we had a very good first interaction. So I guess one lesson to learn from this is that you have to be open to meeting new people. You have to listen to your gut. And if something is going well, you should continue it, not just get out of the situation, but capitalize on it, keep on talking. And, I didn't do it because I was planning on making a company with this guy. Okay? I was just doing it because I love my research. I love science. I love to talk about this. So we talked about this, and there was no agenda whatsoever. And this is how best startup companies are formed. When people know each other and they have no agenda, they can, do something for each other, such as this discussion. When there is nothing on the on the stake. You're not trying to gain something financially from the other person. It's just a natural conversation due to a natural, actual real interest. This is, I think, a very good sign if you ever try to make a company, if you know somebody like this already, right, from your life. So yeah. So then this is a long story. I could tell more details about this story, but maybe not so interesting or we don't have the time. So 4 years later, at some point, he asked me if I want to make a company. And I said yes. And then we made Ziva Dynamics. So that was a long answer to your question. But yeah, that's what motivates me and how my life and my projects and my research directions were shaped.
No, wonderful. You had a very interesting beginning of your career. And before we go on and talk about your academic accomplishments and your startup, let's talk about physics-based simulations. This is your expertise, particularly the deformable objects. Could you explain why simulating deformable objects is so challenging?
Yeah, first of all, what are deformable objects? So any object in our universe is at least a little bit deformable. Deformable means that something is not rigid. The object can bend, twist, under external forces and change the shape. And so you can imagine our human body, every tissue is a little bit deformable, right? The muscles bend, deform. Even the bones are a little bit deformable, even though they're much stiffer. Human hair, can bend. The clothing bends and deforms as the person is using it. So do trees and plants. There is oceans where the water is moving. So deformable objects is really a very, very broad class of objects because it encompasses everything, right, that there is in the world around us. And so why is it challenging to compute how specifically the objects deform? So simulating deformable objects means that you subject a deformable object to some concrete boundary conditions or some external forces. For example, there may be a human muscle, which is a squishy deformable object, and it's attached to, let's say, another bone. So one end of the muscle inserts into a bone, and the other end, let's say, inserts into another muscle. And then as that bone and the other muscles move, it pulls right on this muscle, causing it to stretch. And then the muscle may also fire at any moment of time. And if it fires, then it contracts. And so to simulate deformable objects means to compute the shape of this muscle when it's subjected to firing or when it's being pulled by other muscles. Okay? So you know the geometric shape of the muscle when it's undeformed. You know where it's attached. So it's constrained to a bone or to a muscle. Maybe there are some additional forces that are being applied to this muscle, such as gravity, for example. Maybe this muscle is colliding, is in contact with another bone or another muscle. So that contact is causing some forces that are pushing this muscle. And then out of all of this information, the task is to compute the shape of the muscle. What exactly is the shape of the muscle when it's being pulled and so on. Okay? So this is what it means to simulate deformable objects. And why is it so challenging is because in order to truly solve for the shape of the muscle in any particular configuration or under any particular forces, it requires actually solving some nonlinear partial differential equations that are very well known in physics. They are the Navier equations, not the Navier-Stokes equations. Those are for fluids, but for three-dimensional solid deformable objects, they are just Navier equations. And those equations are not solvable by human beings on a piece of paper. So you can't just write down that equation and do some mathematics, do some calculation by hand and arrive at the final result, at the final three-dimensional shape of this muscle. Instead, you have to actually use a computer to solve that partial differential equation. You have to use something called the finite element method to convert this mathematical object, the partial differential equation, into the computer language so that then the computer can solve for the shape of the muscle. And how exactly you do that, right? That conversion from a mathematical partial differential equation into something that the computer can solve is highly non-trivial, and there is many different ways to do it. It's not just this one way. So how exactly you do that so that it's efficient, efficient meaning that the computer can quickly solve for the shape. Okay? So you don't want to just solve for the shape, but you want to solve in a reasonable amount of time so that you can practically simulate this and compute how the muscle is actually moving in a human body. So that's why it's challenging, okay? Because first of all, mathematically, we cannot even solve it. There is not just one way to do this, and we don't want to just do it. We want to do it accurately, and we want to do it quickly, right? We want to do it with the least amount of computing resources. So ideally, we want a very high accuracy, but very little computational cost. right? And achieving this good trade-off is very, very difficult. There's not like just one way to do this. There are many different ways. And so much of the research, literally in deformable objects, is about perfecting this process. Of course, that's kind of the core of my research. I mean, it's something that I do a lot, but then there are many other things that I also do. So it's not the only thing that I do, although I did spend a fair amount of time working on this. And in particular, I worked a lot on simulating non-linear materials. And so biological tissue, such as human muscle, has this property that if you pull on it with a force, it will of course bend or extend. But if you pull with double the force, the deformation will not be doubled, right? The deformation may be tripled or maybe not tripled, but it will not be exactly double. So there's not a linear law that if you make the force 10 times stronger, the deformation is 10 times larger. There's some non-linearity that kicks in, and capturing that non-linearity, measuring it in 3 dimensions, figuring out the non-linear law inside the human tissue between displacements and forces. This is a wide open problem, and really there are no good techniques at the end of the day to capture this full nonlinearity in the human tissue. So that's another reason, for example, since you ask why is it difficult and challenging, it's because capturing the elasticity, right, of the muscle, how much it resists actually when you're pulling on it in different directions. This is something very difficult to acquire, right? So this requires also good experiments. It requires equipment in a laboratory to do this. Now I'm talking a lot about the muscle, but you can imagine this is a problem applied also to elasticity of plants. Okay? Maybe you want to measure how bendable is a leaf on a tree, or maybe you want to measure how bendable or how deformable is some mechanical component in an engine. Let's say you're building a car engine and there is a hose, some kind of a hose that supplies a liquid into the engine, and you want to prototype the engine, and this hose needs to find its way, it needs to be inserted just in the right position, and you want to somehow predict, right, whether a hose made of a very particular rubber material will be able to be inserted just in the right position and stay in its place, and will it be touching some other surface in the engine which is maybe hot, so it shouldn't do that. Predicting these things is another application, right? Because again, you have a deformable object, in this case a rubber hose, which is positioned somehow in the engine, and again the rubber has certain properties, so when you pull on it, it will deform more or less depending on how strongly you pull. So it's very similar to the human body. And so there are many such applications. Then in robotics, you have soft robotics. So some robots are not made just out of rigid parts. They have also soft components, deformable components. So how can you predict the deformability of those components when they're grasping something? For example, if you make a robotic human hand, you don't want to make the hand out of a steel, material. You want to maybe pad, those fingers with something soft so that it's easier to grasp objects with a robotic hand. So what's the deformability of those elastic pads that are coating the core rigid hand of the robot so that the grasp is as stable as possible? And so these are some applications of my work.
Very interesting. And just a little bit more on the applications. I mean, you already gave us some examples, but would you like to expand a little bit on that? Maybe give us some more important applications of this.
Sure, yes. So one application that I'm very excited about is digital humans, digital twins of real humans. And what this means is to create a digital replica of any organ in the human body, or maybe the entire body as a whole even. So maybe let's first talk about the human body as a whole. So nowadays, there is this metaverse thing, which essentially is an evolution of virtual reality. Virtual reality is this field where we create a virtual replica of everyday objects or particular experiences. Maybe you go to some fantasy land, you go to some other planet to explore what it would like to be another planet inside virtual reality. And then that virtual world is recreated in front of you, and you can have this immersive feeling that you are there. And that's nothing new. This has been around for a long time, since at least the 1990s. But we live now in an era where virtual reality has a second comeback, if you will. So it's a very popular topic nowadays. There are many companies pursuing this. They are making virtual reality headsets and also augmented reality headsets. And people are using those headsets and having fun. And then there's this idea of a metaverse. Okay? So let me maybe use this opportunity to explain what exactly is the metaverse, and because it is a little bit mystical and could be easily misunderstood. So we already have VR, but we are using the VR mostly for those applications that I listed, right? So transporting ourselves to some fantasy world, different kinds of experiences, touching some object, maybe performing training in VR. If I'm a firefighter, let's say I want to learn how to put out a fire, I may train in VR how to operate a fire extinguisher. If I'm a technician and I want to learn how to service, let's say, an airplane part, let's say an engine of an airplane, I may train in VR. If I'm a surgeon and I want to learn how to perform some dangerous procedure on an actual human being, I may train in VR so that if I make a mistake during the training, I don't actually harm, the human. So these are these applications of VR, right? But now there's this evolution of VR into the metaverse. And what is the metaverse is this idea that VR should not just be used for these applications that I just listed, but it should also be used for human-to-human communication. So human-to-human communication, of course, mostly is in the real world. You just talk to the person one-on-one. But the other kind of very important human-to-human communication is when humans are not together in the same space. Okay? So you and I are now talking. You are in Switzerland. I'm in California, United States. And we're able to talk, right, and have a conversation. And of course, obviously, there is many such conversations daily around the world. It can also be with video and so on. But the idea of the metaverse is to make this communication extremely realistic. So let's actually talk in virtual reality with other human beings that are in other places in our planet. They may be in the same city, but maybe half an hour away. I may be talking from my home to students at my university. Or I may be talking from Los Angeles to Slovenia. Or maybe I'm talking, if I'm a doctor, which I'm not, I could be a doctor, right, seeing a patient in some rural county in California. Yeah? So maybe I could be a doctor at some hospital in Los Angeles and seeing some patient that is located maybe 2 hours north of LA in the countryside where maybe the health system is not as good as it is in LA. And you can also imagine that maybe I could be talking to a patient in a third world country, right, and trying to help them. So the idea of the metaverse is to make this interaction extremely realistic, right? To make it as seamless as possible, to make it be almost as if you actually met the person in the real world. And so this requires high quality three-dimensional computer graphics so that you can actually see the other person in 3 dimensions. You are wearing the VR headset and inside you see the other person in full 3D, extremely realistically, exactly like they are. And they're not just sitting there and doing nothing. They are moving, right? So they are acting and moving like they would be in the real world. And so you're able to interact with them very naturally, seamlessly, right? This is the idea of the metaverse. Building this kind of a technological future where it's super easy to stay in touch with friends and family. So many of us, like I mentioned, I left Slovenia. I live in the United States now, but I still have a family in Slovenia. So meeting them in VR in 3 dimensions would just be wonderful. I have right now, in Slovenia, I have 2 nieces and 1 nephew. And so it would be wonderful to be able to just interact with them in this manner. And this technology doesn't exist today, but that is the metaverse, right? Building a full 3D digital replica of humans and then interacting with them. And so now, if you think, how can I build a highly realistic digital human that looks just like an actual human? Well, in order to really truly simulate a human, you need to understand the human body and how it works. You need to understand at least the musculoskeletal system, because the shape of the human body is dictated by the shape of the underlying muscles and the fat primarily, right? The other organs also important, but they don't contribute to the external shape as much as the muscles and the fat and the skin, of course. So can we somehow build a digital replica of all of those biological systems, put them all together, and then as the person is moving, the muscles are firing correctly. And this is not just in the torso of the body, also on the human face. There is facial animation. Can we recreate those expressions so that they're very realistic, so that I really feel like I'm talking to an actual real person? So this is the metaverse. And you need deformable objects everywhere, right? Because the human tissue is very deformable. Yeah, so that's one very exciting application, because once it succeeds, it means that we will be able to interact with people very seamlessly, even if they're far away. Which, for example, means that if you have a long-distance girlfriend or boyfriend, you will be able to meet them in VR and continue that relationship with ease. There won't be so much pain, of this long-distance thing on when can I fly, when we will see each other. No, you will just go into VR and just talk to them in VR. Same thing for friends and family, and same thing for business, for work, right? We will be able to interact with coworkers in this way. Businessmen will travel now businessmen travel, right, to another city to sign some kind of an important deal. And they mostly do that because before they sign the deal, they want to meet the person with whom they are making the deal so they can see if that person is trustworthy, whether, they will screw me when I sign the deal or they will not screw me. So you go there, you shake their hands, you look them into the eye and so on. But maybe if we have metaverse, it will not be necessary anymore. because even though the metaverse will not be exactly the same as the real thing, you will be able to interact with the person at such a deep level. You will be able to see their body language and facial expressions and what the eyes are doing. You will obtain 95% of the information just in the metaverse. So you will never need to fly a plane, to do a business meeting, which means that there will be substantially less air travel. There will still be some because people will always love to travel around the world, but the business travel will decrease, which means that there will be fewer flights, which means that there will be fewer CO2 emissions into the atmosphere. So if you go from the beginning, physically based modeling, the metaverse, deformable objects is saving the climate, right? Because there is going to be fewer CO2 emissions into the atmosphere. So this is some very exciting application, and it's also great to see big companies such as Meta, stand behind this, announce that this is a big thing. They even renamed, the name of the company used to called Facebook, and now it's Meta. And why did they do that? Is because they realized that the metaverse is the evolution of Facebook. Facebook is also a medium for human-to-human communication, but it's mostly two-dimensional, because you're typing messages on a computer screen, you're posting photos, you're not actually interacting with the other person in 3 dimensions. So they realized that the next version of, the next generation of human-to-human technology is going to be 3-dimensional in VR. Right? That's why Facebook renamed itself to Meta and has a huge group inside Meta building virtual reality and designing, this kind of a system that I'm talking about. So we can expect something like this to hit the market in the coming years, and it will be world-changing. It will mean that anybody can live in any place in the world that they choose. If you like tropical countries, you love to live in a warm climate, maybe you will move to Hawaii and work for a company in Slovenia and still have the same experience as if you lived in Slovenia in terms of being able to interact with your coworkers. Or the other way around, people could live in Slovenia but work in other countries. Yeah, this is all related to kind of connecting the planet, right? The planet is becoming smaller and smaller, if you will. People are connecting more and more, and it's just a natural process. So, okay, that's one application. Then applications are also in medicine, and I like those applications a lot. And so they are about figuring out how the human body acts, and now we're maybe talking more at the level of an individual organ. Let's say there is a certain surgery that needs to be performed on a patient. I mean, there are many, many examples, but let's say hip joint replacement surgery could be a good example. This is a pretty serious surgery, and you could plan for this surgery in advance by taking advanced medical imaging of the person, and then before you even perform the surgery, of course, you will look at those scans, and this is routinely already done today. But what maybe is not done today routinely, but maybe should be done, is to actually build a digital replica of the entire surgical site, including all the bones and all the soft tissues, and simulate the surgery in advance, specifically to this particular patient. So concretely for this concrete patient, for the shape of their anatomy, try to get some educated guess, or a very precise educated guess, about how the surgery will actually proceed, what will happen. Is this surgery on this particular patient maybe a little bit dangerous because there is a particular vein very close to where you need to cut the body, right? And so you need to be careful about that, right? Predicting these kind of things. Dealing with the more difficult surgeries could be done when they preoperatively, meaning you will pre-plan for how it could be done. And for that, you need high-quality deformable objects so that you can accurately predict what the human tissue is doing.
Yeah, there is a lot of exciting emerging technologies in virtual reality and AI. And while you were talking about the metaverse and the digital twin, it just came to my mind that recently I've been to the Science Film Festival in Switzerland, and they played a documentary, Eternal You, which kind of explores this concept of keeping people alive during digital avatars. I mean, which in itself is a bit of a question of ethics and morality, but I guess this is just something that I wanted to say while we are on the topic.
Can I just say something about ethics and morality? Because I think it's I don't want this to come across like we're just stupid and unaware of the dangers of this technology. We scientists, right? Of course, we are very well aware that all of this could be misused very badly. But there are many technologies in the history of humans that could be potentially dangerous. Actually, the whole field of artificial intelligence is potentially dangerous. And before that, we can imagine some technologies in the past that are equally dangerous. For example, nuclear weapons could be, a good example. So, and even everyday objects are dangerous if they are misused. For example, an axe, that you use to chop the wood is potentially dangerous, right? If it's misused. So what are we supposed to do? Are we supposed to just ban people using tools and access? Because we should ban all the knives, in this world. Nobody should ever be allowed to use a knife because knives could be used to harm people, right? So it's this kind of a dilemma. And I think specifically for the metaverse, there will need to be some legal frameworks. Okay? So this is not just a problem for computer scientists. There's a problem for the whole society. So people from legal professions will need to find a way to keep this safe. It's also a huge privacy issue, obviously. So a lot of privacy law will need to be involved. Probably there will need to be legislation. So parliaments will need to enact legislation to properly protect this, design laws, to protect the society. And also on the technology front, there will need to be many technological solutions to address this problem, right? So it's not like we're just doing this and nobody's thinking about those consequences. I just want to, mention that. Sorry to interrupt.
Oh, no problem. And of course, this has also been already discussed on our podcast. We had a couple of episodes with guests working in AI, and every time we discussed the privacy issue and the topics. So yeah, I do agree that this is important to always bring up. But yeah. Back to you. And I really want to ask you, as a professor, what are your main accomplishments or some of the things that you're most proud of?
Thank you for the question. What I've done, so I published over 50 scientific papers, but maybe I'll say that one thing that I'm proud of is my work on simulating human hands. So in my laboratory, we had a 5-year-old project funded by the National Science Foundation, the United States National Science Foundation. Mentioning that because there's also a Swiss National Science Foundation, but this one is the US National Science Foundation. It was a project on creating a digital twin of real human hands, meaning take a real human hand, we scanned it with MRI, magnetic resonance imaging, on clinical MRI scanners at the USC Keck Hospital here in Los Angeles. And then from that data, from the MRI data, we built a highly realistic three-dimensional representation of the human hand. So we acquired the shapes of the bones and the muscles, the shape of the hand itself, the skin, and then we didn't just acquire a static image, we also put the hand into the MRI scanner in a bunch of different positions, and in this manner we obtained information on how the tissue is moving inside the hand when the hand is being actuated. So, and then we put all of this together and built a digital replica of the human hand where you can actually deform the human hand. So you can articulate the human hand and the computer calculates the shapes of all the musculoskeletal organs and other organs inside the hand. So as you're actuating the hand, some muscles are firing, there are tendons that are pulling on your fingers. We compute using mathematics, right, and physics and computer science, the shape of those organs. And in this way, we are able to understand how exactly does the human hand function. So we were able to obtain some insights into that, and this is the first such system in the world. It's the first time in the world that somebody has actually animated the interior of the human hand, at least at such level of precision, and in a manner that actually matches the medical images, matches the MRI scan of the hand in 6 representative poses of the hand. So that's one thing that we did with my students and that I'm proud of. I've done a lot of work on simulating real-time systems. So a lot of work on figuring out how to solve those nonlinear partial differential equations of elasticity rapidly. How can I design a computer system to not just solve them, but solve them in real time? Real time means that you have some very, very short amount of time to predict the shape of an object, such as 1 millisecond. This would be very typical. 1 millisecond of time for the computer to compute the shape of the hand based on the positions of the joints of the hand, or to compute the facial expression on the body based on some text that the person is reading. So these kind of things I've done. Also, I've done a lot of work on capturing the biomechanical properties of human tissue. And I have done a lot of work, or I was the pioneer on a field called model reduction for elasticity systems. This started already during my PhD with Doug James and continued on throughout my career. And that's essentially a new technique to, I don't want to get too technical here, but to figure out some low-dimensional space in which you can better compute and resolve elastic objects. So yeah, this would be kind of a few things, but in a career of a scientist, it's usually not that there is one eureka moment, right? And you've discovered one thing. I mean, there are scientists like this, but most of science is just grinding and grinding and grinding, for years and years, incrementally improving things, doing things better and better and better. And then one day when you look at this, it's like, oh my God, how could I ever do all of this? It's like 20 years of research suddenly in front of you and many diverse applications and so on.
Vega FEM is also one of the projects in your lab, and you also already mentioned it before. Do you maybe want to speak a little bit on that?
When I was a PhD student at Carnegie Mellon and later a postdoc at MIT, I noticed that there is no good software for three-dimensional elastic objects. Meaning there was some software, but either it was commercial software, so you couldn't really obtain the source code, or it was too simple and not really very powerful. I just started, when I was doing my research, I was producing a lot of good research code that I was using for my papers. But then at some point, I realized that this code could be useful also for others. So I started cleaning up my research code and started releasing it for free to the world under a very permissive BSD license, which essentially means that anybody can do with that code whatever they want. So including companies can use it commercially. And of course, other scientists and researchers can use it. So this is a software library for three-dimensional solid elasticity. It can compute the shapes of deformable objects. It can compute how the objects vibrate in 3 dimensions, what shape they assume under specific boundary conditions or force loads. And it's something that I first published, I think, in 2009 as the first version. And then over the years, I improved it. So it's a free software library. A little atypical because most professors, they don't really release the code from their projects, although nowadays that is changing and it's becoming much more common than it used to be. But back in the days, it was relatively rare. So I just published it online and kept improving it over the years so that other people in science and also industry can use it. One day, I searched for who is actually using it, because it's been now 15 years of Vega FEM. And I was able to find 60 academic publications written by other people that downloaded Vega and used it not just as a citation, not just as an honor courtesy to me, but they actually used it for experiments, right? So they actually used it in a scientific laboratory to do research or solve their own research problems. Yeah, and maybe I should mention that the name of Vega comes, of course, from Yuri Vega, the Slovenian mathematician. I was thinking of what would be a good name, and I just thought of him because I think that if he lived today, he probably would like computer science and would like to, solve some mathematical problems with computer science. So I just, in his honor, and because I am Slovenian, I named this library Vega FEM. But it's a very well-known library nowadays. People in my field, they usually know it or they've used it. Or so often nowadays when I go to scientific conferences, once I went to a very trivial example, but I went to a restroom, right, to the toilet, basically, at some academic conference, and I was washing my hands, and some student walked up to me and he was like, "Oh, wow, you are Jernej Barbič, I saw your picture on your website. You made Vega FEM. Thank you so much. I used it for my research." These kind of things happen. So yeah, that's Vega FEM.
Do you want to share some of real world applications of Vega FEM?
Yeah, they are all of the ones that I already mentioned right before, because it's a general purpose solver for 3-dimensional solid elastic deformable objects. So it's very efficient, lean on memory, very well documented also. It comes with a manual. So it's all of the above, simulating human tissue, simulating plants, simulating mechanical components. Anytime there is a 3-dimensional deformable object and you want to simulate it, you can use this library.
Wonderful. So we covered your career, very successful career as a university professor, but you also have co-founded a startup, Ziva Dynamics, whose name is also Slovenian origin. Do you maybe want to start with explaining where the name comes from?
Yeah, so Ziva Dynamics is a startup company that I co-founded in 2015 together with James Jacobs that I already previously mentioned, and also another guy, Chris Gotzel, who is a businessman. So, and then I led the company as the chief technology officer and also board member. The company existed from 2015 until 2021, and then it was acquired. It was purchased by some big American company working in the field of entertainment and computer games. But where the name came from is when we were making the company in 2015, we, the 3 founders, we were trying to come up with a good name. And it's not easy to come up with a good name for a company. And it's actually extremely important, because if the name is kind of exciting, sexy, if you will, right? Then the company will naturally just garner more attention. And in a way, it's very unfair, right? You can pick a very bad name and have amazing technology, and you will get a lot less attention. And it may even make a difference between the company succeeding and not succeeding. Or you can pick a great name and have bad technology, and then you will get some attention, okay? So what's in a name? Yeah, so we were thinking about this name, and we had, like a Trello board with many candidate names. We spent like hours, discussing this, and we couldn't come up with a good name that was not already taken, because in the North America, most obvious natural names are already taken, and you don't want to infringe on somebody else's name and get into a lawsuit later. So we really couldn't come up with a name. And then I said, well, I'm obviously they knew that. I mean, that I'm from Slovenia. They were both Canadian, by the way, Canadians. So I was saying, well, how about we pick some Slovenian name? Because this name is likely not going to be used, in North America. And so then they said, okay, write down a bunch of Slovenian names. And I wrote down a bunch of Slovenian names. And I remember there was Podoba, like an image, and there was a few other Slovenian names like this, which they loved, and they were pronouncing Podoba, and all that. It was funny to me. But then I started listing also actual, given names like male and female. And at some point I listed Ziva. And I told them that this is a goddess in Slavic mythology of fertility. And they immediately loved it when they heard that there's something fertile, because a startup is supposed to be, fertile. Okay, it's supposed to produce something, right? And so they were like, yeah, that's it, And then Je was too hard, okay? So we just removed the hat, and just left Ziva. And so, that's how we picked the name. But the company itself was producing very sophisticated software to generate creatures. Creatures means animals, also humans for film. Yeah. So this was a holistic solution to create a creature. Okay? So say you want to make a film where there is a dog, let's say, a very cute little dog in the film. And of course you could, make the movie by filming a real dog. But sometimes in movies you have something dangerous or something that's not really easily filmable. And so you actually create a digital dog. Right? You create a dog by creating the anatomy for the dog in 3 dimensions, and then you simulate the muscles and the skin, and then you render this dog using 3-dimensional computer graphics, and you have this amazingly looking dog that when people watch the movie, they will never know that this is a digital dog, not a real dog. And so this was tool to execute this process, right, from the beginning to the end. That's what the company was doing. And we ended up being used on over 60 films. So there is 60 well-known films out there that have digital creatures in them that were done with the software of my company.
That is amazing. And looking back, how do you think that Ziva's simulation technology changed the approach to character creation in the entertainment industry? And what do you think that the future holds for digital characters?
Yeah, so Ziva built a tool set that is easy to use, and most importantly, that is available to many artists around the world. So the kind of technology that we put into Ziva has existed in one shape or form at top film studios around the world, but only in a very, very small number of top studios. Okay? So I'm sure ILM already had such a system. They built such a system in-house. And actually, had I taken that job at ILM that I mentioned at the beginning, I probably would have been contributing and building that internal ILM system, okay, that was and still is available to the internal artists at ILM. But the mission of Ziva was to make this technology much more broadly available, right? So because anybody could just pay a license and download the software and start using it. So we ended up having, over 500 companies, right, from around the world use this. And it could be companies that are very simple, like a one-man band company, somewhere in some countries, somebody is trying to make a commercial, maybe not even a movie, like maybe a less ambitious project, and they want to place a cat into the commercial, or they want, to do something that maybe a real cat cannot do, right? But it still looks funny. So they could download this. And so I think the major contribution was that this toolset now became available to the artists around the world. So it democratized this technology. So it wasn't locked just at a few top studios. It was available broadly. And of course, because whenever you make a product that's broadly available, right? Something that random people on the internet, maybe not completely random people, but people with skills, in digital art, but people that do not have skills in physics and mathematics that they want to use, you can imagine that many things can go wrong, right? The user experience must be very polished. The software must be very stable. The manuals must be really clear. There must be good examples. And so this pushed us to make the software very, very stable and very bulletproof. And in my opinion, the quality of our software eventually surpassed the internal quality of those softwares at those top companies, just because we were focusing on this and really polishing it over many years based on user feedback. So the end result is that there is just a lot easier nowadays to make these digital creatures for film. And films are more entertaining, more realistic, more fun. And yeah, that's kind of how it affected the world. And another thing is also that it inspired people for what it can be done, so filmmakers are able to tell stories that previously they couldn't tell, right? Just because they didn't have the resources and time and money. Now with this tool, they can do this. And it also, the company demonstrated that such technology is possible, because it's first of its kind of broadly available technology. And I'm sure there will be competition. There already is competition. So companies started copying us and putting similar things into their own products. This is very natural and very normal. So it just means that, the world has a technology that is enriching our lives that it otherwise wouldn't have. And a lot of artists are now talking about three-dimensional. They didn't used to think so much about anatomy and how to build creatures with anatomy. But now artists around the world are studying anatomy, thinking about how muscles move. So there is more interest in that field. Recently, I even found out that some physical therapists are interested in these simulations because it teaches them how muscles move, and then they can use that knowledge to help patients after an injury. So in medicine as well. Yeah. So, but mostly the company was not doing products for those fields. It was doing products for film. So in film, I think we kind of brought the films to the next realism level, right, through this software.
Yeah, very interesting. Yeah, we discussed also something similar in one of our previous episodes on human-machine interaction. But I want to ask you, what was your favorite part of being a part of a startup or co-founding a startup? It must have been a very interesting and very different experience of being a professor. Is that also maybe something that you want to do again in the future?
So I told to my wife and to everybody that there is two things that I can do in this life. One thing I can be a university professor and a scientist, but the other thing that I can be is a startup entrepreneur, right? Because I just absolutely love everything about startups. And I'm still in touch, of course, with startups. I follow this field, sometimes go to startup events. It's just extremely, extremely exciting to build something new. It's like you're climbing some very tall mountain. So because I am from northwestern Slovenia, right, from Soča Valley. I did go in my youth to the mountains in the winter, in full gear. And it's kind of like that. It's an exciting, very, very exciting thing, to do. It's challenging. You're using advanced technology, but you're also dealing with all the everyday, kind of in quotes, trivial, unquote, problems of the company, right? Dealing with investors, dealing with people that don't believe in your technology, dealing with customers that are impossible, difficult. Customers that one day they say this thing, the next day they change their mind. Dealing with, as a small startup, with larger companies, and what's your relationship to larger companies? A large company may come along and say, oh, I'm so interested in your technology. And then you as a small startup are honored. Oh my God, this important big company has shown some interest in my tech. Maybe they will buy me. You already see dollar signs. Oh my God, they're going to buy me, right? Things like that. And then, they see something and then they go and they ask you questions, how does this work? How does it work? And you tell them, and then a month later, they just disappear and you never hear from them again, right? Things like that. And then you're like so sad. And then 3 days later, or maybe a week later, you get a new customer and you sell and you're happy. Not sell the company, but sell the product. You secure a new customer and then you're happy. And so it's this ups and downs, this kind of a roller coaster kind of a thing. I think for somebody who is, who has an advanced degree in science, but at the same time, they want to interact with the world, they want to deal with kind of real life. Like they need to be street smart, not just book smart. I think this is a wonderful landscape for somebody to try, for somebody to enter this space, because you may end up succeeding, right? You may end up building some amazing product that will enrich human lives, at least to some degree, right? So this is why I'm excited, about this field. It just unlocks kind of a new dimension to life, if you will, right? It's kind of very interesting new experience that most people, unfortunately, never get to experience, these dynamics. So, but yeah, if somebody's listening to this and they have an advanced degree in science and they are thinking of maybe commercializing this, I would encourage them to try it. Of course, you need to get some business skills because it's not easy. Maybe do an MBA or just at least read a lot about business, or partner with somebody who is an MBA and co-found a company together. And I think if you have a good product, if you think really, really, really hard about what the world needs and what would be something manageable that you can actually succeed, but at the same time important that people will pay money for, I think you should go for it. let's not have, startups be run just with people who dropped out of college, okay? Which is a cliche here in America, that if you want to have a good startup, you have to drop out of college, right? Like if you're not a college dropout, you're not supposed to do a startup because you don't have it what it takes. This is somehow, there are actually even some investors in Silicon Valley, Peter Thiel, for example, that are advocating dropping out of college so you can do a startup, right? So I'm trying to put a little bit like an opposition to that, an opposing view that actually we, people with PhDs can also do startups, right? And we can do them really well. So, don't be discouraged, by the people that say that, advanced knowledge is not useful in the real world. It is extremely useful. And you have the skills to do it, more so than people that didn't go to college or that don't have a PhD.
I would agree. I also think that people who have a PhD should not be discouraged to go into startup area. Another thing that is very exciting that I also wanted to bring up in this conversation, even though we will slowly have to wrap up our conversation, is that you worked on The Hobbit. You already mentioned this, and this was when you were a visiting professor in New Zealand in 2013. Do you maybe want to share a little bit more about your role and, I don't know, some of the challenges, how it was working on the movie?
So, just first to give some timeline. So in 2013, I already was an assistant professor at USC, living in Los Angeles, but I didn't have my startup yet. So the startup started 2 years later, right, in 2015. But I had already met James Jacobs, right, in 2011. And James Jacobs and a friend of his who were working in the same unit of Weta Digital invited me to come to Weta for a summer for 2.5 months to be what they call a visiting professor. So this company, Weta Digital, is located in New Zealand. It's actually probably, I would say, I'm not sure the most advanced technological company in New Zealand, but it's a very big kind of major technological employer, okay, in New Zealand. And they are doing a lot of things right that I think other companies should copy. So if somebody in Slovenia from some large company or even medium-sized company that is producing amazing technologies, listening to this conversation, here is an idea for you. Why don't you reach out to some top professor in the field of your company, maybe somebody who's Slovenian or maybe even not, and ask them to come to your company for 2 months or 3 months over the summer to just be an embedded professor or visiting professor. And just have this guy come, to the company and ask them all the questions about the research and try to do some tech transfer. Try to, compensate this professor appropriately, of course, because nobody's going to come for little money. But it doesn't take that much, in my experience. You may be surprised that some people may actually come and show an interest, because for professors, it's amazing to see the company firsthand, because you see the actual internal processes that are happening in the company. You can see how the work is organized. You can see the types of positions, right, the types of jobs that people do. You can see what they do. You can see next to an amazing engineer, and you can see what they do on a daily basis. So I was able to benefit. I said yes, and then I lived, or stayed in Wellington for 2.5 months in 2013. And I was going, of course, to Weta every day, and I was in this team of about 50 people that was building creatures for Weta Digital Films. And when I was there, they were working on The Hobbit, the movie. Hobbit, the Desolation of Smaug, that Hobbit. I was, at the time, I already had Vega FEM, and I showed it to them. And I said before that there are academics using it, right? So I found 60 research projects in academia that use it. But at Weta, they were very interested in it. And so they already had downloaded and were using it. But they asked me more questions about this, and I improved it for them, made it a little bit better when I was there. And at the end, it got integrated into their engine, and it was used on the film. Got film credits for The Hobbit. So that was a nice experience. And later on, when I made the startup, it also helped me because I was able to see, the different kinds of jobs that they do, the different people that work there. I also got good connections, because the company is very strong. So it was employing top engineers. And those people were not from New Zealand. I mean, some were from New Zealand, but most of them were from all over the world. Like many of them were European. Actually, I would say at Weta Digital, most technical staff was actually, I would say, European. From some country in the European Union. That was the largest group. So I was working in New Zealand with people from France and from Austria and from Germany. There was somebody from Serbia. And then there was also the second largest group, I think, was Americans or Canadians, people from North America, and then there was a lot of Australians. So it was a very interesting working environment also, just from that point of view, just seeing all of these different cultures, coming together and making technology for film. Yeah.
Wow, super exciting. But this conversation is slowly coming to an end. So maybe let me just give you one last question, which would be if you have any recommendations for any books or maybe podcasts or maybe some last words before we finish.
Recommendation for podcasts. Actually, I will admit that I watch quite a lot of YouTube and I enjoy watching things. I watch Lex Fridman a lot at MIT. I find his interviewing style very good, meaning that he's asking the right kind of probing questions. So I watched probably 50 podcasts by him, I will admit. So that's one thing that I love. This is maybe a little unrelated, but another podcast or YouTube channel that I love is a chess channel by Agad Mator. This is a Croatian chess channel, which is in English, and I love... I used to be a kind of chess player and active chess player back in Slovenia, and I still love the game and I sometimes play it. So I find it exciting to listen to the biographic stories of the chess players and how they came to be, Bobby Fischer, Casablanca, and all of those life stories really inspire me because these are people that are a little different than myself, but they still work in some kind of an unusual profession, if you will, right? And they need to use their brain to succeed. And it's interesting to listen to how they get the ideas, to play this game. So that's something that I enjoy a lot. I also am a big fan of Michio Kaku, who is an American professor of physics, lives in New York, and he talks a lot about technology and talks about the future of technology. So he's a futurist. He makes bold predictions about how our planet will evolve in the future, what our civilization will look like in the future. Michio Kaku, check him out. He's extremely smart, very, very bright, and I tend to agree with most of his predictions.
Thank you very much for your recommendations. And I have to say, 50 podcasts from Lex Fridman, that is quite a lot, especially considering that his podcasts have a really long format, normally multiple hours.
Well, I'll admit that sometimes if the guest is boring, I will just skip over sections. But I listen to this like late in the evening, maybe before I fall asleep, at the end of my day, just to get a little inspired about what other people are doing.
It was very nice having you on the podcast. And thanks a lot for taking the time to come here and to share your experiences and all of your work that you have done so far. And so thank you very much.
You're very welcome, and thank you for inviting me, and best of luck to everybody.